So let's move on. There is this international conference that was held in 2018 trying to come up with defenses against adversarial examples. And there were a lot of papers being written. I'm going to go through 7 of them. In addition to this paper, it's going to be 8 papers. So if you don't understand this slide fully, it's okay. And I don't expect you to. This is just an overview of what was happening at that time. This is the first one, thermometer encoding, trying to defend against adversarial examples. The idea is that you want to break linearity. Their idea is, and if you manage to break linearity, then your adversaries are not going to be able to backpropagate through your neural network to reach the input image. And maybe because they cannot backpropagate, then you're stopping them from attacking you. That's an idea. You have an image. Each image is a bunch of pixels, and they have multiple channels, perhaps red, green, blue. What you're going to do is you're going to do a transformation on your input, on your image, directly on your image. You're turning a scalar, so this is now a scalar, into a vector, and this has a name. This is L-dimensional, and let's just call it thermometer encoding. You try to lose as few information as possible. This is going to end up being lossy, but you don't want it to be too lossy, not to mess up too much with your image. You're turning a single scalar into a vector, and how are you going to do it? You're going to look at the value of your scalar, and if it is bigger than the entry that you're interested in from this vector, divided by the size of L, by the size of your vector, you're going to set that to be 1, otherwise 0. Here's an example, a scalar, which is 0.66 or perhaps 6666. You can represent it by a 10-level encoding, where whenever k, in this case k is 1, divided by 10, which is going to be 0.1, is less than 0.66. So that's a 1. And it's going to happen up until the 6th one, 0.6. And beyond that, it's going to end up being 0. So hopefully you are not losing that much information. You're just losing this 6%. But the cool thing is that now this is hopefully a discrete operation, a bunch of zeros and ones, and then it's going to be harder for your adversary to reach your input image through gradients. And they were claiming at that time that this is a good method, and it makes sense to defend against adversarial examples. Another paper, input transformations, is similar. You start to randomly drop pixels from your image, and you restore them. Now you have some dropped pixels in your image. How do you restore them? You look at the variance of your entire image, and then try to adjust these pixels that are missing to minimize the variance or the variation in your image. At the same time, you can reconstruct your image by replacing some small patches with patches of clean data having the same class. Again, similar idea. You don't want people to be able to reach your input image through backpropagation and then change it. This one, they are not claiming that they are trying to defend against adversarial examples, but they're actually trying to find it or try to detect them. Is this an adversarial example? Yes or no? Is there a metric for doing that? That's called local intrinsic dimensionality. It's a metric. Let's go through it. Let's first define a distance. So don't worry about the first line. Let's define a distance on your feature maps. You take your image, push it through multiple layers of neural networks, first layer, second layer, up until the jth layer. You can take another image, push it through the same architecture. Now you can compute the L2 norm. You can treat this feature map as a vector. You can treat the other feature map as another vector, and you can compute their distance, L2 norm. And that's your distance between two images. So you're using your neural network to define a distance. And as I mentioned, this is just a composition of layers from 1 through j. Now, what is LID for this particular layer? For this distance defined for this particular layer, jth layer, this is just the ratio of, so it's going to become clear here. So Ri is the distance between sample x and it's ith nearest neighbor. As soon as you have a distance, you know that you can find your neighbors, which neighbors are closer to you, which ones are further away from you. You take a look at x, and then your ith nearest neighbor, you plug them inside your D, and that's going to give you your Ri. Rk is the same. It's the kth nearest neighbor rather than the ith. And then what you're going to do is you're going to train a logistic regression classifier to detect your adversarial examples by looking at their LID features. Okay? And this LID features, it's a set where you are changing, where you are cutting your neural network. Are you cutting it after the 5th layer, 6th layer, 7th layer? And that's going to give you a set. And you can use that as your features to train this logistic classifier. Okay, and K is a hyperparameter that you choose. You're going to say that I'm going to look at my 10 nearest neighbors, and then you're computing this log of the ratios. You can use that to find adversarial examples or to actually detect them. So this is not a defense mechanism. This is just for detecting them. You can actually come up with a defense mechanism out of these LID features. How? You can put your LID features, maybe put a weighted combination of these LIDs, and that's going to give you your loss function that you can put in your robust optimization. Okay? So you're going to use these LIDs to come up with perturbations and add them to your training data. But maybe because these are K nearest neighbors and K is a discrete choice, and finding the K nearest neighbors is a discrete problem, maybe because of that, your adversary is not going to be able to reach your input X through backpropagation because these are discrete functions. You don't know what the derivatives are. And because of that, maybe your neural network is more robust in the face of adversarial examples. Another idea is to have a stochastic activation pruning. Introduce some stochasticity in your architecture. For instance, you can randomly drop some neurons of each layer with probability proportional to their absolute value. If a neural network is really active, you use that to come up with the probability that you're going to drop that neuron. So it's similar to dropout. And whatever values that are left, whatever neurons that are left, they have to compensate for the ones that are absent. So you have to rescale them the same way, or rescale their weights. It is the same way that you were rescaling the weights after dropout when you wanted to put that into production. So there is this idea of a stochasticity, and maybe because your architecture is stochastic, your adversary is not going to be able to guess it, which architecture you're using, and therefore they're not going to be able to reach your input through your neural network. The other one is getting similar randomization. For stochastic activation pruning, you were introducing randomization in your layers. Here you can introduce randomization for your images, for your inputs. If your input is a 229 by 229 image, you can randomly rescale it to be either 229 or 300 or 331, up until 331. You just randomly rescale it. Now your image is going to be either too big or too small. If it ends up being too big, actually, if it ends up being too small, smaller than 331 by 331, you're just going to zero pad it so that it has this size. And that's just randomizing your input. Another idea is to use generative models. And what does your generative model is going to do? You're going to take an image, you're going to push it through a neural network, and then out comes another image. So you're imagining images similar to the image that you're conditioning on. One idea is this pixel CNN generative neural network, which we are not going to have time to go through. Similarly, there is the GANs, which we are going to go through next semester. And these are conditional adversarial neural network, generative adversarial neural network. So forget about this adversarial. These are conditional generative models. If I give you an image, you're going to give me as many images as I like from you by keeping generating images that look like the image that I just showed you. That's the idea of generative models. You're going to keep generating images. And both of these are going to create a manifold in the space of images So manifold, you can think of it as a curve in 1D or as a surface in 2D, etc. But these are high dimensional images. It's going to learn a manifold, and then you're just going to project your adversarial examples back to that manifold. So you have two problems here. One is you have an image, you have a very deep neural network, which is this GANs or pixel CNN, very deep. It's going to give you a manifold now. You're projecting onto that manifold. The projection is a discrete operation. And being discrete, then you're avoiding reaching your input image. That's one problem. The other problem is these are deep neural networks, and they're going to lead to vanishing and exploding gradients. If your adversary tries to attack you, they're going to have difficulty. They're going to have to deal with vanishing gradients or exploding gradients. Because the deeper your neural network is, you're going to multiply multiple matrices together. And whenever you do that, you're either going to explode or vanish. So multiplication is bad. And being deeper is bad because of these problems. What are you doing? What is the big picture now? All of these papers, all of these methods to defend against adversarial attacks, they're just trying to hide gradients or make it harder for you to compute gradients. And why did we need gradients? Because, for instance, a method like fast gradient sign method was trying to take the gradients of a loss function with respect to the input. And if you manage to obfuscate those gradients, then your neural network, your attacker is hopefully going to have difficulty attacking you. But as the title says, this is going to give you a false sense of security. You're going to do that. You're going to assume that because you did that, you're now secure against adversarial examples. But in reality, people can still attack you and avoid all of these techniques. How? Let's first classify what we just did. Options 1 and 2 are shattering your gradients. Your gradients either don't exist or you have some discontinuous functions, and they're going to end up being incorrect. You're backpropagating through a discontinuity. You're shattering your gradients. This other one is similar if you add it to your loss function because of this k nearest neighbor. These ones, stochastic activation pruning and randomization, you're just randomizing your network, your input, and maybe because you have a stochastic gradients, your adversary has to deal with the stochastic gradients, they're going to have difficulty. The other one leads to vanishing and exploding gradients, because to reach your input, you have to backpropagate through a longer network. But there are ways to deal with all of them. And that's the idea of backward pass differentiable approximation. Whenever you have a non-differentiable layer, like what you have here, this is a non-differentiable layer, or if it is differentiable, your derivatives are not useful, you can approximate that layer by a function. For instance, fi is the one that is not differentiable. You can approximate it by a g function and then perform backward pass. Rather than going through the one that has difficulty giving you derivatives, you go through g. And that's what your adversary is doing. As an example, for all of these, you can do that. Let's take a look at this example, the thermometer encoding. Your tau, first you can define tau hat, which is gonna try to, whenever you're bigger than k over L, set you to be 0. Whenever you're smaller, set it to be 1. So you can change that function that you had here to come up with thermometer encoding with just a minimum and a maximum function, which we know how to take derivatives of. They're going to give you good derivatives. They're discontinuous, but they're not that bad. It's similar to having a ReLU function. This is exactly your ReLU, and we know how to differentiate it. There is going to be the floor operation, because after this minimum and maximum, you're going to have some decimals left still. You can kill them by using the floor operation. Now, what you can do, the only thing that is causing us a trouble is this floor operation. We can just remove it. And that's going to give you an approximation to your tau function. So rather than using tau, you're going to use tau hat, which is differentiable. And then you're going to be able to attack thermometer encoding. The other one was about randomization. You randomize your neural network. The idea is, rather than looking at a random neural network each time, look at the average neural networks and come up with your gradients. Because in the end, in average, you want to attack them in expectation. You want the gradient of the expectation of a neural network performing some transformations on your input, like these randomization. These are random. There is a distribution on them. Compute your gradient over the average model. And then this is equivalent to averaging your gradients, okay, because these are all linear operations. They're differentiation and expectation, they're just linear operations. And then you can attack number 4 and number 5. For this other one, 6 and 7, you're going to do the same thing, similar to what we did here with backward past differentiable approximation. You're just going to approximate what the neural network is doing. If there are some nonlinearities because of those projections onto the data manifold, you can just remove them. Don't project. Like here, don't do the floor operation. Don't project. And then you can do a reparameterization to deal with the vanishing and exploding gradients. Maybe your gradients are vanishing and exploding in the X coordinate system. Change your coordinate system to another one, and then that's going to help you deal with vanishing and exploding gradients. So this one is just a paragraph in the paper that I want you to read, the mathematical formulation. But the idea is that as soon as you reparameterize, you're going to be able to get rid of the vanishing and exploding gradients and reach your input. Any questions? Yeah, so the idea is these are 8 papers. 7 papers are trying to come up with a defense. The 8th one is telling us that all of these are trying to obfuscate your gradients, and then there are ways to avoid them. And the idea is that I don't want you to understand every single one of these papers because perhaps it is not worth it. But what is worth it is that if you come up with a defense mechanism on your own, and then you're obfuscating some gradients, then your method is going to be avoidable. So that's the big picture. And these are the techniques to avoid that.